BKW Physics. I'm Mr. McConley, and today we're going to continue our energy discussion with the conservation of energy. And the first picture I want to start with is on the left-hand side of the board right here, and we're just dropping a ball in this picture. And if we're dropping that ball, I could assign some different values for energies to the ball. If this spot right here denotes the point where you just let go of the ball, so you're holding it, you let go of it, what is the actual kinetic energy that this ball possesses right as you let go of it? Zero. Thanks. How about the potential energy? Well, the potential energy, it's hard to say what the number is because I haven't given you the mass or the height, but we could assign a number, let's just make it up and say it's 20 joules of potential energy, just so for the sake of argument. Well, then as the ball falls, if this right here represents the halfway to the ground point, then if that's halfway to the ground, halfway before it hits the earth, then what would the kinetic energy be at this point? 10. Thank you. And the potential energy? 10. It makes sense, says some people. And when it finally reaches the ground, and I'm not talking about once it hits the ground, once it stops, once it balances. I'm talking about the fraction of an inch, fraction of a millimeter before it hits the surface of the earth. What's your kinetic energy? It should be right around that 20 joule number. And the potential energy, because now you don't really have any height anymore, is zero. Well, the idea here, conservation of energy is the title, is that energy is conserved. Energy cannot be created or destroyed, it only changes form. That's a law. So, 20 plus 0 is 20. 10 plus 10 is 20. 20 plus 0 is 20. Energy is being conserved. Now, it still works in between, it's just that in between is much harder to figure out what the numbers are. Alright, that situation seems clear and straightforward. Let's go over here to this picture here with a little cart that's rolling down a ramp. Now this picture is a little bit different because if we start assigning numbers the same way, let's say the kinetic energy right at the top is 0, the potential energy right at the top is, let's use that number 20 again. Now something has changed here, because if I go down to the bottom and I assign some realistic numbers, the potential energy, of course, is 0 because you're at the lowest point now. But let me assign a number for kinetic energy of 18. Why would I do that? Well, I would do that because that would be realistic. In actuality, if that's 20 up there, you don't get exactly 20 down here if you're rolling something down a ramp, because some of the energy went somewhere else. And where'd that go? That's the question. Well, we call it Q in physics, capital Q. And what Q means is it's called internal energy. And usually we're talking about friction or heat. Those are the typical things that make up internal energy. In other words, when you roll something down a ramp, there's ball bearings on the wheels, and there's wind resistance, and what that adds up to is it adds up to some of the energy gets kind of lost. But I don't like to use that term because remember, energy cannot be created or destroyed, it only changes form. So basically energy goes from being potential, most of it goes to kinetic energy, but some of it, in this case we'll say is 2, now I'm making up these numbers, but some of it, in this case 2, is internal energy. Does that make sense? Alright, so another situation is a pendulum. And in a pendulum, we'll assume this is a frictionless pendulum, so we can ignore the Q this time. We'll just forget about it. So this thing's just swinging there. It's got no friction. Of course, that's a little bit made up, but roll with it. So, A. pendulum is at its highest point. Therefore, what is true about its potential energy? Well, it has to be a max. So again, you want to use the number 20 again? So 20 joules of potential energy when it's at point A. Now since point A is the point where it stops before it goes back down, what's the kinetic energy?
0.
Okay? Follow it through at the bottom. This is the point where the pendulum is moving the fastest, so it has the most kinetic energy, which would mean it must have 20 if we're using our numbers. And the potential energy is 0, and that's hard for some people to wrap their mind around because the pendulum's still up in the air, right? Yeah, I get that, but according to the constraints of this system, the pendulum can't go any lower. Unless that string breaks, it's not going any lower, so we can say that potential energy based on this situation is 0. And then we can come over here and say, okay, the kinetic energy is back to a 0, and the potential energy is back to a 20 joules. That all making sense to everybody? Alright, switching gears real quickly, I'm going to erase the board, and I want to draw another picture for you. And I want to finalize one of the equations. The first picture I want to draw for you is actually a graphical relation where something like this. This axis represents the ET, total energy of the system. And this axis represents position, we'll say. So if in this situation, if we start with this line being the kinetic energy line, and if it's starting down here, we'll say the kinetic energy is actually starting at 0. So what's a situation where your kinetic energy is starting at 0? This could be the ball drop, the first picture. So you're starting at 0. As the ball falls, the kinetic energy increases. Okay? And then you could actually have the ball bounce again. Okay? And in that case, you would reach a maximum kinetic energy and then it would drop off again as the ball rose back up to its highest height after the bounce. That's the kinetic energy line. Now I can add to this another line, which would go something like this. And this line, this red one, would represent the potential energy. Because we noticed from the picture how they kind of work in opposition to one another, as the one's going up, the other's going down, and vice versa. And the final line that you could add on this picture would actually be a dotted line. And this dotted line that I have shown in blue would be the sum of the potential energy and the kinetic energy, or we could say it was the total energy of the system. This is assuming that we don't have any friction, right? Any Q. So this is a picture that helps you kind of wrap your mind around how one goes up and the other goes down, but the total remains the same. That's the conservation of energy. Now the real equation, if you go to your reference table, is written this way in your reference table. It says ET equals the potential energy plus the kinetic energy plus Q. That's the way you're going to see it in your reference table. But depending on the situation, a lot of times the regions will say ignore friction or ignore internal energy. And in that case, you can kind of do this, which is what we've done with our picture. So for today,